Okay, good afternoon everyone, and thanks to the organizers for giving this opportunity. And I am Sivasurender Chandran, in short Siva. So I am in IIT Kanpur for the last 3.5 years. And today I'm going to discuss with you some of the experimental results that we obtained on understanding bacterial turbulence and how harnessing the activity of the flow allowed us to understand the different microscopic dynamic regimes underlying the bacterial turbulence. So when I say we work, of course I don't work. So it's an intelligent graduate student that I have. It's Dhananjay, and who has carried out all the experiment that I'm discussing here with support from another graduate student, Hemlata, and that's my collaborator in the biology department who feeds me with the bacteria so that we can do experiments with them. And thanks to all the funding supports who have been gracious in supporting our activities. So with that, let me quickly give a background. Like I think this audience don't need a lot of discussions on active matter or on collective dynamics. But I think when you have a dense active fluid, so collective dynamics has been seen across various scales, and also various work has indicated signatures of turbulence in such collective dynamics, starting from nonlinear velocity flows and efficient mixing of components, and the existence of long range coherent flow structures, right? So this is something which is known, and given this background, what we were asking is what is the microscopic dynamics underlying the emergence of such bacterial turbulence. Like when you are having high densities, you start seeing the collective flow structures. So how do they emerge, and what is the microscopic dynamics relevant for that, right? So given that, we have some pre-work, from simulations from the group of Samriddhi and Siddharth. So they have done simulations based on one or two equations, and what they indicate is that there will be a presence of anomalous diffusion and intermittent Levi walks, which allows them to distinguish conventional turbulence from active turbulence, right? So with that background, let's go into my experiments, and we do experiments with Bacillus subtilis, a smooth swimmer. So these are not really run and tumble like bacteria, though they swim more continuously. And then in our experiments, what we have done is we have taken suspensions of different concentrations where we have controlled the bacterial concentration, and also we have put in few representative passive colloidal particles so that we can trace both the colloids to get the Lagrangian description of the fluid flow, and we can remove the colloids and trace the overall fluid flow dynamics, so to get the Eulerian flow, and to essentially feed each other descriptions to that, right? So, and our only variable that we are going to have is I'm going to change the concentration of the bacteria, which I give with this number, which is called as the optical density. But effectively, the range that which we have changed the bacterial concentration would roughly correspond to varying from 0.01 to 0.5 in terms of volume fraction, right? And our experimental setup is that we just put a simple sessile drop, and these bacteria are aerotactic bacteria. They run towards the air surface, and then they perform the 2D dynamics, and that we try to capture by putting them under the microscope. Right. So with that, I just show you two representative videos. On the left, you see very less fraction of bacteria, and on the right, you see a huge fraction of bacteria. And the spherical particles are the colloidal particles. On the left, you can see that the colloids are just being kicked by bacteria swimming around. And while on the right, you can see that the underlying fluid goes through a collective dynamics, and the colloids are going for a tour as driven by the underlying fluid flow, right? And then I can look into the trajectories of the colloids, and now at the same scales, 40 micrometer, you can see when the concentration is very low for the bacterial fluid, the trajectory is very small, and if you zoom in, and then you essentially see kind of similar to a random trajectory. But then with higher concentration, you can see much longer persistence flows, which are also becoming loopy, as as you can clearly see, right? So then we went ahead and we extracted the overall velocity profiles of all these colloids, and if I plot the mean of this velocity as a function of the concentration of the underlying bacteria, you can see initially the variation is not much, and beyond some bacterial concentrations, the colloids start showing much larger velocity, indicating some such some kind of transition to collective dynamics, right? And then now we can remove all the particles, and I only look into the fluid flow, and I can look at the, like track the fluid flow velocity by this simple PAV kind of tools. I'm not going to describe more into the detail. So let's say I can just like get the flow, velocity at each and every pixel as we are looking into, right? And that's what I'm showing you here for the same two concentrations, when very low concentration of bacteria and very high concentrations of bacteria, and the heat map shows the velocity at those positions. As you can see, at low concentrations, the velocity is like high at very small areas, but at very high concentration, you start seeing the emergence of this kind of collective coherent flow structures, and the white lines are the streamlines for the flow, and you can see that they're kind of getting mixed over long range, right? And now I can get the velocity distribution of the fluid element. I can compare the mean velocity of the colloids and mean velocity of the fluid, and both of them essentially follow similar behavior, and that is underlying the transition of isolated to collective dynamics. This is something like people have seen earlier. We are not the first ones to show, of course, but then now, since we can now have collective dynamics over a long range where we have different velocities of the overall flow, now we can go into the Lagrangian traces and start looking into the mean square displacements and try understanding the nature of dynamics, right? So now let me guide you through this MSDs. Like at no bacterial addition, we have more or less Brownian motion throughout. With smaller addition of bacteria, you have initial super diffusive motion, which eventually relaxes to random motion. But then if you put in larger, and when the transition has become collective dynamics, you can see initially ballistic diffusion, which goes via kind of a super diffusive behavior before eventually becoming random, and that's what the running slope analysis also has shown. So now we were thinking what does this intermediate super diffusive behavior indicate? So then we went back to the video, and then now we are looking at this colloids diffusion, and now these are being kicked by this different vortices which are being produced. And maybe the answer is by if you are looking at the long time trajectory of a single colloid and plot the velocities. Now you can see when I normalize it to the mean velocity, so they are jumping over orders of more than an order of magnitude, which suggests that the kind of presence of intermittent kind of dynamics in the system, right? This intermittency can now come from fat non-Gaussian tails, or power loss in terms of if I look at the run length or look at the waiting time distribution, and that's what we have looked into. And when we look into this, I think, let me not go into the details, but if I look into the waiting time distribution for different range of concentrations, at very low concentration when there is only isolated dynamics exist, so the waiting time essentially followed what is expected, like Gaussian dynamics. And if I go to the boundary of the collective dynamics, we can clearly see the presence of a power law over orders of magnitude here, and that slope, if I compare with the slope that we got from the mean square displacement, that effectively tells me that this is a Levi stable statistics. And then this is something that Samriddhi has also shown in his simulation. But what we are seeing something beyond is that at very higher concentration, there is a transition from this kind of Levi walk to a Gaussian type of dynamics. And we asked how do we understand these transitions? And since now I get the velocity field, I can get the velocity correlation and look at how the temporally it is evolving. And now I can look at the correlation functions which are evolving, and the longest time essentially speaks about the fluid correlation time. If I just mark those fluid correlation times here, you can see that where we are seeing only power law, the fluid correlation time is much beyond the experimental time window, while we are seeing this transition, the fluid correlation time essentially traces the point at which the transition from Levi walk to Gaussian occurs. And just to capture this little more clearer, so here I'm renormalizing the probability of run times, and you can see that for fluid correlation tau by tau f less than 1, we see Levi walk, and for larger than 1, we see Gaussian fluctuations, right? So with that, I think we are showing clear existence of three microscopic dynamic regimes: ballistic and anomalous and random. And the anomalous dynamics is mediated by intermittent Levi walk. And also, as we can show that by controlling the activity, we can see different dynamics at different time windows, and hence harnessing activity allows us controlling the transitions. And that's the reference. This work is already in archive. And with that, I thank you.
Only one question.
Okay, so for this two-dimensional fluid created by the bacteria, what are the Euler equations actually? Does one know what these equations are? And from that, can you extract anything about the this Levy motion and so on?
So I think 2D Eulerian like equations are known. I think your like what we can possibly rely on, for instance, what Samriddhi has done is this 2D dynamics that own the 2 and Swift Hohenberg addition. So there he could show the existence of this kind of Levi walks, right? And our experiments are supporting that, and now we are trying to look more into the microscopic doings of this and like kind of trying to look for if there is this continuous time random walk with fractional Brownian noise and so on, and some recent results seem to indicate that, but we have not yet completed the story there.
Did you look at the distribution of displacements? Like you showed
Yes,
the time,
so we have looked into the distribution of the run lengths. So now when we plotted run length as a function of the run time, we see a beautiful linear of this cumulative probability, which says that we have a finite velocity of this Levi walk.
Okay, let us thank the speaker.